It is the night of 9th November 1940, and somewhere over the English Channel, a young RAF pilot is doing something that should, by any reasonable calculation, be impossible. He is flying blind. Not metaphorically blind, genuinely blind, with cloud thick enough to obscure his instruments. Enemy flak bursting in orange blossoms he cannot see but can feel rippling through the airframe, and a heading that leads directly into the heart of occupied Europe. He has no way of knowing exactly where he is. He has no way of knowing with any certainty where the German radar stations are. What he does know, or more precisely, what the boffins back home are beginning to suspect, is that those radar stations, the proud technological backbone of Hitler's Atlantic Wall, are not quite as invincible as the Germans believe. The Germans called their coastal radar network the Kammhuber line, a dense, overlapping web of detection equipment that stretched from Norway down through Denmark, the Low Countries, and into France. It was a system of formidable sophistication, built around the Freya and Würzburg radar sets, capable of detecting incoming aircraft at ranges of up to 120 kilometers and guiding night fighters to within visual range of their targets with unsettling precision. By 1941 and into 1942, Bomber Command was losing aircraft at a rate that threatened to render the entire strategic bombing campaign unsustainable. Crews spoke of the German radar as though it were some kind of malevolent omniscience, an invisible eye that never blinked, never slept, and never missed. What the Germans did not know, what even most British scientists did not yet fully understand, was that their radar had a weakness, not an obvious one, not a weakness born of poor engineering or inferior materials. It was a weakness hidden in the fundamental physics of how radar worked, a weakness that would be exposed not by a deliberate research program, not by a brilliant flash of wartime inspiration, but almost entirely by accident. The story of how Britain discovered that narrow strips of metallite foil, dropped from aeroplanes in their millions, could effectively blind the most sophisticated radar network in the world is one of the strangest, most consequential, and least tidily heroic episodes of the entire war. It is a story about a discovery made too soon, then deliberately suppressed, then reluctantly unleashed. And when it finally was unleashed, on the night of 24th July 1943, over the city of Hamburg, it worked with a completeness that left German radar operators staring at their screens in bewildered, helpless silence. This is the story of Window. To understand why Window mattered, you have to understand how desperate the situation had become for Bomber Command by the middle of the war. The Kammhuber line, named after General Josef Kammhuber, who designed and expanded it, functioned through a system of overlapping radar-guided boxes, each covering roughly 35 kilometers of airspace. Within each box, a single night fighter was directed by a ground controller who could track both the bomber and the intercepting aircraft on his Würzburg set simultaneously, talking the fighter in until visual contact was established. The system was elegant, methodical, and extraordinarily effective. In 1941, Bomber Command's losses to night fighters began climbing with a consistency that made the statistical projections deeply alarming. An aircrew completing a full tour of 30 operations, already a proposition that required considerable courage even to contemplate, faced odds that, by some estimates, gave them roughly a 1 in 3 chance of survival. By 1942, with the expansion of the Kammhuber line and the growing sophistication of German night fighter tactics, those odds were worsening. The aircraft being lost were not abstractions. They were Halifax and Lancaster bombers, each carrying a crew of 7, representing hundreds of hours of training, thousands of pounds of manufacturing cost, and 7 lives per aircraft. The RAF's existing countermeasures were limited. Jamming devices could disrupt specific radar frequencies, but the Germans were capable of switching frequencies, and a jammer powerful enough to be effective also served as a useful beacon, advertising the location of the aircraft carrying it. Evasive routing could reduce exposure to the Kammhuber boxes, but only by adding fuel consumption and reducing bomb loads. Bomber stream tactics, where large numbers of aircraft flew the same route in a compressed time window to overwhelm the capacity of individual radar boxes, helped at the margins, but they required precise timing and coordination that deteriorated over long distances and in bad weather. What was needed was something that could defeat radar not by fighting it, but by confusing it, not by being invisible, but by making everything around the aircraft equally visible. The concept, in retrospect, is beautifully simple. Radar works by sending out a pulse of radio energy and detecting the faint echo that bounces back from a solid object. If you could flood the air with thousands of objects that each returned their own echo, the genuine return from a bomber would be lost in a snowstorm of false signals. The radar operator would not see nothing. He would see everything, an undifferentiated mass of returns with no way of distinguishing the real from the artificial. The question was, what material could create such an effect economically, in the quantities required, and in a form that could be carried aboard aircraft and released in mid-flight? The answer, it turned out, was already sitting in a laboratory at the telecommunications research establishment at Malvern, and it had been sitting there, theoretically understood and practically demonstrated, since early 1942. Joan Curran, a physicist working within TRE's team, had been investigating the radar reflective properties of various materials as part of a broader program of electronic warfare research. What Curran discovered, through a combination of theoretical calculation and practical experiment, was that strips of metallized paper, or aluminium foil, cut to a length equal to precisely half the wavelength of the radar frequency being jammed, would produce a disproportionately large radar return. The physics involved is the same phenomenon known as resonance. The strip, tuned to half the incoming wavelength, effectively acts as a receiving and re-radiating antenna, amplifying its apparent size on a radar screen by a factor that has nothing to do with its physical dimensions. A strip of aluminium foil, roughly 27 centimeters long and 2 centimeters wide, roughly the size of a large bookmark, would, when falling through the air, present a radar return comparable to that of a large aircraft. A bundle of such strips, each tumbling independently as it fell, would create a cloud of returns that moved and shifted unpredictably, mimicking the kind of fluctuating, uncertain signature that no experienced operator could confidently call a formation of bombers, rather than atmospheric interference. The mathematics were straightforward. The Würzburg radar operated at a wavelength of approximately 53 centimeters, meaning the optimal strip length for that frequency was roughly 26 to 27 centimeters. The Freya radar, which operated at longer wavelengths for long-range detection, required correspondingly longer strips. A single bundle of strips, roughly 2,000 of them, packed into a small rectangular packet weighing around 1 pound, could, when released, create a radar return equivalent to a heavy bomber. A stream of aircraft releasing such bundles at intervals of 1 per minute could generate a cloud so dense and so extensive that the radar picture behind them became, for all practical purposes, useless. Curran's findings were confirmed, expanded upon, and classified at the highest level almost simultaneously. And then, for over a year, nothing happened. The reason for the delay was one of the more grimly ironic episodes of wartime scientific bureaucracy. Almost immediately after Window was demonstrated to be effective, senior RAF and government figures became convinced that using it would be counterproductive. The argument ran as follows. The Germans, once they saw what Window did to their radar, would immediately understand the principle involved. They would then manufacture their own version and use it against British radar during the anticipated German bomber offensive. Britain's own radar network would be blinded. The cure would create a worse disease than the original condition. This was not an unreasonable concern. Both British and German scientists were perfectly capable of deducing the principle from a single operational use. The question was one of relative advantage. Which side stood to gain more from the mutual availability of the technology? And for months, that question was batted between committees, argued in memoranda, and referred upward without resolution. If you're finding this interesting, a quick subscribe helps more than you know. It genuinely makes a difference to this channel and means we can keep making stories like this one. It was, in the end, a combination of mounting Bomber Command losses and a shift in the strategic situation that finally forced the decision. By mid-1943, the German Luftwaffe's ability to mount sustained offensive operations against Britain had been significantly degraded. The bomber threat that had been the primary argument for withholding window had receded. Bomber Command's losses, by contrast, had not. On 15 July 1943, Air Chief Marshal Arthur Harris formally requested authorization to use window, and on 23 July, approval was granted. The target chosen for the first operational use was Hamburg, Germany's second-largest city, a major industrial and port center, and a city that had been raided repeatedly but never struck with the full weight of what Bomber Command could now bring to bear. Operation Gomorrah, as it was named, would involve 4 major raids over 10 nights. The first, on the night of 24 July 1943, would be the test. 791 aircraft took off from bases across eastern England that night. As they crossed the coast of Germany, each aircraft began releasing its window bundles, one bundle every minute, pushed out through a chute in the fuselage, the packets splitting open in the slipstream, and the individual strips separating and beginning their long, tumbling fall through the dark air. What the German radar operators saw on their screens was unlike anything they had encountered before. Where previously they might have tracked a bomber stream as a coherent formation, they now saw their screens filling with returns. The Hamburg Flakversuchskommando, the experimental anti-aircraft unit stationed around the city, reported that their fire control radar had become, in the official report's carefully neutral language, inactive. Night fighter controllers attempting to vector their aircraft onto bombers found that the individual returns they were tracking dissolved into the general mass of interference before they could complete the interception. One German controller, recorded in intercepted communications that were later translated and preserved, was heard to transmit simply, "I cannot control anything. Everything is confused." The losses on that first raid were remarkably low by the standards of the Hamburg campaign. Of the 791 aircraft dispatched, 12 were lost, a rate of approximately 1.5%, compared to the 4 to 6% that had become grimly normal for deep penetration raids. The bombers reached their targets, released their loads, and came home in numbers that felt almost surreal to the crews who flew that night and survived. The Germans, as anticipated, immediately understood what had happened. Within days, Luftwaffe scientists had recovered bundles of window strips from German soil and confirmed the principle involved. German engineers quickly began producing their own version, which they named Duppel, after the location where the first recovered strips had been analyzed. Duppel was physically identical to window in its essential design, strips of aluminized paper cut to the appropriate half-wavelength dimensions. The difference was one of timing and operational context. By the summer of 1943, the Luftwaffe's capacity to mount large-scale offensive operations against Britain was a fraction of what it had been in 1940 and 1941. Duppel was used in raids during Operation Steinbock in early 1944, the so-called Baby Blitz. But the scale of those operations, never more than a few hundred aircraft, was insufficient to replicate the overwhelming radar saturation effect that window had achieved over Hamburg. German radar operators, trained and retrained on the new situation, developed procedures for working around the interference. Experienced controllers learned to identify the leading edge of the window cloud, reasoning that no British bomber would drop behind its own jamming, and to concentrate their attention on returns at the cloud's front. These adaptations were genuine and partially effective, but they never fully restored the Kammhuber line to its pre-window efficiency. The Americans, for their part, had been following British window trials with intense interest. The United States Army Air Forces adopted an equivalent system under the designation chaff, a name that endured and passed into permanent use in the vocabulary of electronic warfare. American chaff differed from British window primarily in its materials and production methods, reflecting the different industrial resources and manufacturing priorities of each Air Force, but the underlying principle was identical. By late 1943, chaff was being used extensively by the 8th Air Force in its daylight raids over occupied Europe, with results that substantially reduced losses to radar-guided anti-aircraft fire. The true legacy of window is one of those historical cases where the impact is simultaneously easy to describe in broad terms and surprisingly difficult to quantify precisely. German radar never recovered its pre-window coherence. The Kamm-Huber line as a unified, systematic defensive network was effectively broken on the night of 24th July, 1943, and subsequent German attempts to reconstitute layered radar-guided defenses were consistently disrupted by the systematic use of window alongside the expanding array of British jamming and deception measures that the RAF's No. 100 group was developing through the same period. Bomber Command's loss rates did not remain at the miraculous 1.5% achieved on that first Hamburg raid. The Germans adapted, and other factors ensured that deep raids into Germany remained dangerous throughout the war. But the baseline was shifted. Window did not make bombing safe, but it made the existing level of danger more sustainable. The raids on Hamburg alone, Operation Gomorrah as a whole, are estimated to have destroyed over half the city's residential area and killed somewhere between 35,000 and 45,000 people, with the uncertainty in those figures reflecting both the chaos of the raids themselves and the inadequacy of German record-keeping in their aftermath. The material damage to Hamburg's industrial output is estimated to have set production back by several months at a critical point in the war. The principle of radar countermeasures that Window demonstrated, that a radar system's fundamental operating mechanism could be turned against itself, became one of the central organizing ideas of what eventually became the discipline of electronic warfare. Every modern military aircraft carries some variant of the chaff dispenser. Every naval vessel carries chaff rockets. The technology has evolved. Modern chaff uses metallized glass fibers rather than aluminium foil strips, optimized for different radar frequencies and deployed in more sophisticated patterns. But the principle remains identical to what Joan Curran demonstrated at TRE Malvern in 1942. Examples of original window strips survive in several British collections. The Imperial War Museum holds samples, as does the RAF Museum at Hendon, where they are displayed alongside the aircraft that carried them and the radar equipment they were designed to defeat. They are, physically, almost comically unimpressive. Narrow strips of metallized paper, a few centimeters long, weighing almost nothing. It requires some effort of imagination to connect these flimsy scraps to the night over Hamburg when they fell in their hundreds of millions and reduced the proudest electronic defense network in the world to a screen full of meaningless noise. Return for a moment to that pilot over the channel on the night of November 1940, flying blind through cloud and flak, with nothing between him and detection but luck and altitude. He did not know about window. It did not yet exist, even in theory, or rather, the theory existed in fragments, distributed across scientific papers that had not yet been connected into a single practical concept. He was flying against radar that was, in that moment, as close to infallible as technology then permitted. 3 years later, the situation had been reversed with a thoroughness that would have seemed fantasy to anyone who flew those early raids. It had been reversed not by defeating radar in any direct sense, not by jamming it or destroying it or outrunning it, but by understanding it, by recognizing that any system sensitive enough to detect an aircraft at 100 kilometers is also sensitive enough to detect a strip of aluminium foil at 100 kilometers, and that this is not a strength but a flaw, exploitable with nothing more exotic than a printing press and a roll of foil. The discovery was accidental in the way that many of the most important scientific discoveries are accidental, not random, but occurring slightly outside the boundary of what was being specifically looked for by someone paying close enough attention to notice what they had found. Joan Curran was not trying to blind German radar when she began investigating the reflective properties of metallized strips. She was doing what scientists do, following the physics where it led, measuring what she found, recording the results. The application came later, after the science had been understood. What followed, the year of suppression, the arguments in committees, the mounting losses that finally forced the decision, is less the story of a discovery than the story of the entirely human difficulty of acting on knowledge you possess, but are afraid to use. The Germans had not developed window independently, not because they lacked the scientific capacity, but because they faced the same dilemma from the opposite side. They knew that metallized strips could jam radar. They knew that the RAF might use the technique against them, and they were too afraid of providing the model for its use to develop it themselves. Both sides sat on the same discovery for different reasons, each waiting for the other to move first. It was Bomber Command's losses that ended the standoff. It was Hamburg that demonstrated the consequences. Window did not win the war. No single technology wins wars. But on the night of 24th July, 1943, 791 aircraft crossed the German coast, and the invisible eye that had watched and guided and killed for 3 years looked out over the sky above Hamburg and saw, for the first time and never quite so clearly again, absolutely nothing. That is what a strip of aluminium foil falling through the dark can do when someone is paying enough attention to understand what they have found.